Hello and welcome back to Calculus 2. Today we are going to talk about 10.3 infinite series and we are going to talk about the exam. Today is the long class, long day, so hopefully we'll get to sort out both of those things. We'll start with 10.3 on infinite series and then move along to see what else we can cover in terms of the review and talk about the exam and everything else. So, last class, 2 days ago, we talked about sequences. Sequence was ordered list of numbers, and ordering was done through natural set of numbers n. That n appeared in the index and represented the location of the term in the sequence. So from last time, sequence was the ordered list of numbers. And the ordering was done through n, so we had an was a0, a1, a2, a3, a4, ... an. Now we said that the sequence can be finite, sequence can be infinite, all of that stuff. So that was the last time. Today we're talking about series. Series is the sum of the sequence. So this is today on the menu. To learn about series. We're learning about the series. Notation for the series has the summation symbol you were introduced to in Calculus 1, chapter 5, 5.1 I believe was when you were introduced to this symbol. And this symbol literally means addition. So, what you have here is notation, well, two of them. One for infinite series, and the other one for finite series. Now, we will not be dealing with finite series at all. I will explain shortly why. But let me first write what this one is. So, summation of an, when n, let's say it starts at 0 and goes to infinity, is simply a0 plus a1 plus a2 plus a3 plus ... plus an plus ... going forever. So this over here, the plus ... at the end, make sure it's going forever. And the sum could be finite, in which case we say converges, or infinite, which is divergence. Now, this is the reason why finite series are not interesting. So I said finite series are boring. Why are they boring? Because they always converge. They always converge. If you have a finite series, that means you have finite amount of terms, you just add them all up. If it's a little bit of numbers, you add them by hand, more you use the calculator, even more use the computer, right? And since it's coming from the sequence, it's ordered, so computers are really good in adding ordered numbers. So we don't care whether we have 5 terms or 5,000 terms. We can add them either by hand or on the computer. So if you have a summation, n goes from 0 to m of an, then the sum is a0 plus a1 plus a2 plus dot 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 plus am minus 1 plus am is the last term. And that's finite. See, it stops at the end. So it will converge to whatever the sum is, and we're done. So not interesting at all. However, divergent ones, the infinite ones could diverge. They could add to infinity, but again, infinitely many terms added, they could also add to a finite number. A little bit counterintuitive, but one of the very important should I say features of chapter 10 is please let go of common sense, because it doesn't sit very well with this section, and we'll test those as we go along. All right, so let's recap. 2 days ago, we said sequence is ordered list of numbers, and ordering was done through set of counting numbers 0, 1, 2, 3, 4, 5. 0 is not a counting number, but we'll toss it in a system, in a set. So we order the numbers, and then now for series, we take the same sequence from before and we just add those numbers. Now, it could be infinite or it could be finite. Now, I do have to talk a little bit about notation, because not everyone, I guess, remembers everything about the sum, which is the sigma notation. So you were supposed to learn this in pre-calculus, then you were supposed to learn it in Calculus 1, chapter 5.1, and now we get to use this, then differential equations, it's going to use it a lot, and so on. If you go on with mathematics, partial differential equations, we'll be using it for every problem, and then whole bunch of your 300, 400 level courses when you transfer out. We'll be using this, especially upper level chemistry, physics, mechanical, electrical engineering. I mean, you guys will be sick of this symbol. So now, what is the meaning of the symbol? Well, if you have a symbol where the counter starts at 0 and ends at 5 of just an, well, that means that this counter will be changing the index, and every time it changes the index from 0 through 5, it will introduce a new term that you need to add. So the first term is a0 when n is equal to 0, and then summation is a plus, and then n changes to 1, so 1, and then you have all of these all the way to the last one, which is listed on top. You stop when n is equal to 5. So n equals 0 through 5, we have 6 terms, because 0 through 5 has 6 numbers. So that takes care of that. You just add those values, right? Now we can have a formula because we know that AN is a sequence of some kind, and that AN has the formula to it. So let AN be n squared minus 1. So what would be the summation n goes from 0 to 3 of AN? Well, it would be summation n equals 0 to 3 of n squared minus 1. So your first n is 0, so you have 0 squared minus 1. Then the next time around, your n is 1, so 1 squared minus 1. And then 2 squared minus 1. And the last term, 3 squared minus 1, because I am ending this problem at 3. And now I just compute these values. That's negative 1 plus 0 plus 3 plus 8 for a total of 10. So this series converges to 10. Well, every finite series converges. Finite when you have a number here, infinite when you have infinity. So every time you have finite number of terms, they just all add together, and you will be able to compute the sum at the end. Now, if you have a summation that starts starts at 0 and goes to infinity of, let's say, 1 over n. We can't start at 0 now because it's 1 over n, so we'll start at 1. You can start at 2 or 7 or whatever. I mean, the problem will require you to start somewhere. We have 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus 1 over 5 plus... And this will go forever, right? It will go forever. And now the question is, does it converge or does it diverge, right? The sum. Because you can't add infinitely many numbers like you could have, like you did here. You had 4 numbers to add in the example before. Now you have infinitely many numbers to add, right? So how do we figure out whether this sum adds or to a finite number, which is convergent, or divergent? Okay, so first, now that we are familiar with the sum, right? You can also look at the properties and so on. Let's talk about what it means to converge and diverge, right? So let the sum start at 0. We can go to infinity. We're not going to bother with the finite sums anymore because we know they all converge. So now we are always, as soon as you have possibility of divergence, you are dealing with infinite sums, right? I mean infinite series. And let's say you have some series, right? We are just going to put this general AN formula in it. We're not going to put a particular one like we did above. Just put the general one. And what we are going to do is we are going to define convergence and divergence of series through convergence or divergence of partial sum, a sequence of partial sums. Now that's way too many words in one for the new terminology. So let's take a look. So let series be something. We don't know what this is, which formula you have, but we do have some kind of a series, right? And let P of n denote partial sums. Could have used S as well, whatever, doesn't matter which letter we use. So now my series is going to be equal to A0 plus A1 plus A2 plus A3 plus A4 plus A5 plus A6 plus dot 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 going forever. Now I want to know what the partial sums are. So partial sum P0 is just A0. Partial sum P1 is A0 plus A1. And that's going to be some number. Partial P2 is A0 plus A1 plus A2. P3 is A0 plus A1 plus A2 plus A3. So all of these are numbers, right? Because remember how when you plug in the values into the formula, the ends, you compute the numbers. So as you can see over here, A0 was -1. Over here, A0 was A1 was 1, right? So A1 over here was 0. A1 over here is a half, and so on, right? So all of those work out to be numbers. So here is your P0, here is your P1, here's your P2, here's your P3. So if you put that in a sequence, you have -1, -1, 2, and then 10. Right? So partial sums are very simple because you first just have a first number by itself creates the first number in the sequence, then you have P1, which is the first two numbers, then the P2, you add these, then the P3, you add these, then the P4, right? So every time for a partial sum, you add one extra member and you get the next number in the sequence. So now we say that series an, n goes 0 to infinity, converges if Pn converges. Now we know how to test Pn, right? It's just a basic limit problem from our last lesson. So this is going to create some kind of a pattern. You use that pattern, you put it together, which is what we did last class. Right, you have a whole bunch of numbers and then you create that an and then you plug that into the limit, right? And that's it. So if Pn converges, then the series converges. Otherwise, series diverges. And we denote that with a D. So now we are technically done with chapter 10. If you don't want to learn 10 special tests that let you skip all of this plus that, right? You are technically done with series because you can always compute partial sums and then, you know, good luck with using those numbers to find a pattern to figure out whether it converges or diverges looking at the limit of the sequence you have. But that's not the ideal way for us to deal with these problems, because computing all of these partial sums and then figuring out the pattern is too tedious. It's too much work. Instead, we are going to learn and memorize 10 different tests for series, and those 10 different tests will tell us whether our infinite series converges or diverges. That's the idea of what we are doing now for the rest of the chapter 10. So you will have one test for sequences. That's the limit one we learned last class. And then there will be 10 tests that you will learn to test whether the series converge or diverge. Those tests are called, there is an integral test, there is a root test, ratio test, there are two comparison tests, telescoping series, geometric series, right? Those two we'll cover today. And then alternating series and piece series, and I got them all. So those are the 10. Now, I already mentioned it once, and I will be mentioning this many times, not just today, but every time pretty much I teach this. If you do not memorize those tests, you will be clueless on what to do. You have to memorize the tests. Now, before you freak out, I will remind you that you learned many derivative rules because you didn't want to bother with the limit definition of, remember the limit h goes to 0, f of x plus h minus f of x over h, right? That's the way to solve every derivative under the sun. But we don't want to bother with those lengthy conversations, calculations. So instead of dealing with all of that stuff in terms of computing the limit and so on, we decided to memorize derivatives of polynomials and exponential and all of that, and then memorize the product rule, quotient rule, chain rule, right? So we memorized a lot in chapter 3 so that we don't have to crank that nasty limit calculation every time we need a derivative, and we need a derivative a lot. Well, for series is the same thing. I gave you here, what you see on the screen right now, I gave you the way to work out every series, in this long and laborious way. To find a sequence of partial sums and then to figure out the pattern and then take the limit of that pattern and see whether converge or diverge, right? So this will solve, this should solve 100% of problems you are ever going to see. Because that's the definition for convergence and divergence of series. But since it's tedious, boring, and a lot of work, right? We opt to learn 10 tests so that we don't have to do this tedious work. Again, you could have just used those sums from Calculus 1, but you went ahead and you learned and memorized integration, right? So that you don't have to do that long procedure by hand. So now, we are going to learn 10 tests, but obviously those 10 tests are spread out throughout all of the other sections of chapter 10. So today, we are going to learn only 2 out of the 10. And those 2 are very special. The other 8 are, some of the most powerful techniques are in the other 8. But we'll see how and why these 2 that we learned today are special. And then as we move along, we'll learn every day, we'll learn 2 or 3 of those tests until we learn them all. And that's technically it. So let's talk about the first one that actually let me just write it. So to avoid long computation plus the limit, we learn, in parentheses, memorize 10 tests for convergence or divergence of series. So those tests are in no particular order. Geometric series test, telescoping, then we have divergence test, also known as nth term. We have integral test, p-series, we have ratio test, root test, alternating series, and two comparison tests, direct comparison and limit comparison. And now you're going to maybe, hopefully not, but now you might ask, well, do we really use all of these? Can we just, say, these are the three that we want to learn and just dump other seven? No. Because certain problem can only be integrated using integration by parts. Certain problems can only be solved using partial fraction decomposition, right? Some problems can be solved two different ways. So you have 10 tests, and each one of them will have at least one situation when only that test works and nothing else. So we have to be very careful, right? And you need to know all 10. Right? Now, obviously, we're covering this over 5 sections, or 6 maybe. So, don't stress you're not learning everything in a day, right? It should take about 2 weeks to see all of the tests, and then obviously, hopefully, you practice every day and, figure out. So let's talk about geometric series. So, from this point on, whatever I write in blood, you immediately memorize, store in your head, understand the way it works, because you will see very quickly in this section. If you know it, problem is done instantly. If you don't know it, you're just going to stare at the page. It is very, very straightforward. So, geometric series. Let sum n goes to 0 to infinity of a r to the n right? So that's the geometric series. That's what it looks like. Now, we are going to have two different situations. One for convergence, one for divergence. In some cases, there is inconclusive. In some cases, convergence is missing. In some cases, So not every definition for every one of those 10 tests is going to look the same. For geometric series, you have the form of what they look like. And then we say the theorem. If R is in between a -1 and 1, then series converges. If absolute R is bigger or equal than 1, the series diverges. And now, so those are the two cases. There's one more thing which I'm going to put different color. If geometric series converges, then the sum is given by S equals A over 1 minus R. There we go. This is what you are memorizing. All of it. Every single line, every single word, every single formula, everything. So if you know this, the problems are a joke. So let's see. Example. Converge or diverge. It's always asking test for convergence or test for divergence or just that's always what it is, right? Test convergence or divergence. That's what we are doing in chapter 10. All right, and the problem is summation of 1/4 to the n from 0 to infinity. That's it. That's the problem. Nothing else is given. Does it converge or diverge? How do you solve the problem? All right, ready? You use your eyes and you look at the series. You determine that R is 1/4. Since 1/4 is in between -1 and 1, series converges and you are done. That's it. So I hope you were sitting down for the solution, right? That's it. You look at the value of R, and if that value is between -1 and 1, the series converges. That's what the red stuff is telling you here. Look at R, and if R is here, it converges. That's all it says. Okay, next example. Summation 0 to infinity of 3 to the n. All right, so R is equal to 3, which is bigger than 1, diverges. Done. Next problem. So I hope you're getting into the spirit of this. If you memorize the definition, you can solve the problem in 5 seconds or less. If you don't know the definition, you can just stare at it and have no clue what's going on, and you will never, there is always a 50-50 chance, right, of guessing the answer, but yeah, good luck with that. Let's take a look at a spicier example. Summation of 0 to infinity of pi divided by e to the n. Right? So your R is pi over e. And that's bigger than 1. Because pi is 3.14, e is about 2.7, right? So when you divide them, you're going to get a number that is bigger than 1. Divergence. On the flip side, 0 to infinity e over pi to the n. R is e to the pi Now that's less than 1 convergence. So visually here, you can put this R on the number line and have these two barriers, -1 and 1. Over here is convergence, and everywhere outside is divergence. The number you have has to fall somewhere, right? And if it's equal to 1 or -1, that's included in divergence. So pay attention, right? Now, when you have convergent series, let's say you have 3/4 to the n, 3/4 to the n. We have to rewrite this first so we see it a little bit better. 3 times 1/4 to the n. So that's basic arithmetic, right? We didn't even compute anything. We just moved the numerator to the side. And from this one, a is equal to 3. R is equal to 1/4. That's less than 1. We have convergence. The question is, what is the sum? Because I did give you in purple formula to compute the sum of geometric series. So, what is the sum? The sum is A over 1 minus R. A is 3. 1 minus 1/4 is 3 divided by 3/4, which is very good. So, what is the meaning of this? The meaning is that the series, which is the sum of all terms, infinitely many terms, the series converges to 4. It means all of the numbers add to 4. All of the numbers add to 4. I will add a little bit here in blue. So this is equal to 3, right? Because the first time is 0, 4 to the 0 is 1. Plus, then you have 3/4 plus 3/16 plus 3/64 plus 3/256 plus going forever. All of that will be equal to 4. That's what it means. Convergence is the sum of all values, sum of all terms of the series. And they can add to a finite number, in this case 4, or they can add to infinity, in which case we have divergence. The last thing we need to talk about geometric series is what happens if the counter here is not 0. That is a big deal. When you are careful enough, and in mathematics you always have to be very careful because definitions are very precise and they mean only one thing, observe that the form that was given to you specifies that you have to start at 0. Right? That is clear. So when you go down here and you look at the problem, n goes from 2 to infinity of, I don't know, 3/4 to the n. I'm going to use the same problem as here, except now I'm starting at 2. Does this change convergence? The answer is hell no. Your r is still 1/4. That is still less than 1. We're still convergent. But the sum clearly should be way less than 4, because if I'm starting at n equals 2, then n equals 0, n equals 1, and n equals 2 are out of the game. Hey, that is killing like 3.5, no, about 3.3 out of 4. So the sum should be, what, about 0.7 actually, right? So we have to be very careful. If you are to just go and compute the sum ignoring this, well, you will again get a 4. But now, I just told you, we are knocking these terms out, because it starts at the term n equals 2. This is n equals 0, n equals 1. Oh, sorry. This is n equals 2. N equals 2. So it knocks out the first two terms. So we have to account for that. So now, this is the part that is the only part that is kind of tricky, right, for geometric series. So if you memorize the definition, and if your geometric series starts at 0, you are done, right? It's done and done. Should take you less than 5 seconds to solve the problem. The issue is when your counter is not 0. So we have to shift the counter back to 0. We must shift the counter to n equals to 0. And that is the procedure that we are going to learn now. Now, this is coming back. Shifting the counter is coming back big time in differential equations. If you have to take that course, pay attention. So we have n equals to 2 to infinity, and I'll put 3 times 1/4 to the n. We already know that we can use that. Okay. I don't like n equals 2. I need equals to 0. So what I'm going to do should be common sense. Subtract 2 on both sides. So that will give me n minus 2 equals 0. Great, I got equals to 0. That's what I actually wanted. But I messed up this. So I'm just going to combine this into a k. So now my new series is going to be k equals 0 to infinity. I hope you understood this conversion here. So technically, no matter what the number is, you will be able to subtract that number on both sides, and then you just define that n minus 2 is k. Now, if you define that k is equal to n minus 2, well, that's a substitution, right? Then when you continue writing, you are no longer allowed to put n over here, because now series needs to be in terms of k. So what goes up there? Well, what's n? N is k plus 2. So now this And, oops. Come on, pen. You can do it. There we go. This and this. Tablet is lagging, and then it's just all right. So I am giving it way too much input and can't handle it. Okay, let's try one more time. I want this to be red so it stands out. Good, there we go. All right, so we used substitution to create this series. Now I want it black, it's red, it's just all over the place. So now I just need to work with this and I'm done. So summation k goes from 0 to infinity 3 times, and now I have 1/4 squared and then 1/4 to the k. Remember, I am not supposed to have anything other than just n or a k there. So I have to peel off that +2, and luckily in basic algebra we have the formula that tells us just use the same base and put a square, because if I'm to multiply these two using basic algebra, the exponents add. So if I want to break them apart as two factors with the same base, right? And then put each exponent on each one. And this is where we get summation k goes from 0 to infinity of 3/16, 1/4 to the k. So now you see that your a is 3/16, right? So that's what goes wrong if you don't do shifting of the counter. You see, it might look like when you look at this that your a is 3, but your a is not 3 because that's not 0. Only when this is 0, this number here is a. Now, since this is not 0, then 3 is not a. But when you scroll here, you see that the counter is 0. That means that this number is a, and I have it right there. So now I can just compute the sum, which is a over 1 minus r. That's 3/16 divided by 1 minus 1/4. I hate writing fractions this way, but such is life. Multiply by 16, top and bottom, to kill the double fraction. And you get 3/16 minus 4. That is 3/12, which is 1/4. It's 1/4. Remember how I said it's about 0.7? Well, I made a mistake because I was counting this term as well. But do you actually see that 3 3/4 is exactly 1/4 away from 4? Right? So if this takes 3.75, then the rest is taking 0.25, which is 1/4. I mean, it has to click together. You can't get something that doesn't fit. And that's geometric series. Be very careful to always have the form for geometric series summation n goes from 0 to infinity ar to the n. And I'm just going to make it clear. I'm going to point the arrow. If n is not 0, we need to shift the counter. back to 0. And that's the procedure up there. I mean, mathematically, it's a joke of a procedure. You subtract the same number of both sides, use the substitution to shift everything else. But the trick is to remember to do it, right? And the last concept for this lecture for today is telescoping series. All right, so this does not have the formula. Well, it does somewhat have a formula. The formula is, now if I don't put anything on the bottom, it can start anywhere. You can start at 2, you can start at 7, whatever the problem, whatever it starts. For geometric series, in order for your formulas to work, you must have 0. If you don't have 0, you have to shift the counter. For telescoping series, you can start at 2, you can start at 9, whatever, it doesn't matter. And you do not have to shift the counter ever for telescoping series. But you'll be annoyed in another way, don't worry about it, right? No free lunch. So, summation, starting anywhere to infinity, is going to be given as, let's say, b of n minus bn plus m, let's say. So it should be of this form. So let's take a look at the problem. This is where we memorize the procedure. And this is the only one of this type where you have, well, actually alternating series will also have some kind of roadmap of a procedure, but this one is very interesting. So summation, let's say 2 to infinity of 1 over n minus 1 over n plus 2. So let's say this is your problem. Okay, so when you have telescoping series, right, you have this subtraction in here, and there is a very interesting way to solve this. What you do is you break your series. I'm going to outline this and then I'm going to erase it and solve the problem. So let me just write something in blue to explain and then I'm going to erase it. Actually, I can write it here and then leave it. So this is going to be my summation from 2 to m of 1 over n minus 1 over n plus 2. And then plus series that will start with this m and go to some value k, 1 over n minus 1 over n plus 2. And for this one, I'm going to put also the limit k goes to infinity. This is known as the tail end. Tail end. So, infinity, right, is forever, right? We cannot put a number to it because every time you put a number, doesn't matter how large you think the number is, you know, the next person can just add 1 and create a larger number. So infinity is, you know, ever growing, ever evolving, and you can never catch up with infinity. So the trick to solve this problem is to make the infinity finite. And that's what this m does. Because this over here is definitely going to converge. We know that about finite series. And then the tail end over here is going to have another finite series, but I'm going to trick that finite series and I'm going to send this k to infinity. We did that in our integrals when we ended the chapter 8 for our improper integrals. Remember what we did? Right? We made it into a finite using a and b, and then we send those, a and b, to different values to infinity, right? So we're going to do the same thing here, except we are going to have a lot more calculations to do. So let's start. We are first going to plug in n equals to 2. We are going to have 1 over 2 minus 1 over 4. Then in the next term, n is 3. That's 1/3 minus 1/5. Then in the next term, n is 4. That's 1 over 4 minus 1 over 6. Plus, the next term, n is 5. So we have 1 over 5 minus 1 over 7. And then we get bored. Now, if you are to remove all of these parentheses and so on, you will immediately see that you can cancel quarters. You can cancel fifths. Right? Let's write more terms. Plus, next one is 1 over 6 minus 1 over 8. Plus 1 over 7 minus 1 over 9. And now let's say we're annoyed. So you see that my 1 over 6 cancels. You see that my 1 over 7 cancels. So do you see that they started canceling everything? And 1 over 8 must cancel here, because the next term is n equals 8, right? So 1 over 8 would cancel there. And then 1 over 9 would also cancel in here. So all of the terms are canceling. What survived? 1/2 and 1/3. Those are the only terms that survived. Now let's take a look at the tail end. What's happening from behind? We are going to write the same structure, right? Now, what I'm going to do here is I'm going to set it up, but I'm going to do this backwards. Remember, I am going now so that my last term is n equals to k. Then the one before that is n equals k minus 1. Then the one before that is n equals k minus 2. Then n equals k minus 3. N equals k minus 4. N equals k minus 5. So this is what I have. Now n equals to k. Well, n equals k, technically you're just copying this one, which is 1 over k minus 1 over k plus 2. So now, the next time, take a 1 away from k. That's 1 over k minus 1 minus 1 over k plus 1. Because when you take away 1, so minus 1 plus 2 is plus 1. So, there we go. And always look at this one and keep subtracting 1 from each one. So now, 1 over k minus 2, 1 over k, 1 over k minus 3, 1 over k minus 1, 1 over k minus 4, k minus 4, minus 1 over k minus 2, 1 over k minus 5, minus 1 over k minus 3, and that will also go plus plus and go forever. So what can we cancel? Well, look for the pairs. Positive 1 over k, negative 1 over k. Negative k minus 1, positive k minus 1. K minus 2, k minus 2. K minus 3, k minus 3. Right? So look, all of these are canceling both terms. As soon as you hit the first parenthesis, it cancels both terms. All of the other ones will cancel for sure with something in the middle. And we have still the same, right, rule over here that these two will cancel in there. What is left after all of this mess? What is left? 1/2 plus 1/3 plus the limit k goes to infinity of negative 1 over k plus 1 plus negative 1 over k plus 2. Now, when you divide 1 with infinity, you get 0. So all of this, in this case, you have to take that limit, right? It's not just, oh, I memorized it because the example said so. No. In this case, the limit goes to 0. Therefore, all we are left with is 1/2 plus 1/3, and that gives us 5 over 6. So, converges to 5 over 6, because we just computed the sum. It's a procedure. You start writing these terms out, and then when you reach a certain point, you stop. Then you work the tail end. Reach the certain point, you stop. Now you say, so when do I stop? Well, go 6 terms. You may want to make a rule, go 6 terms, right? So that's going to be altogether 12 terms, which is what I have in this case. Now, when you start picking up the pattern, you will know how many terms you need exactly, right, before. In this case, I will just tell you that the reason why 2 survive from the front and from the back is because these 2 are 2 apart. That's actually what is going on. So if these are 3 apart, then there will be 3 that survive in front and 3 that survive in the back. If they're only 1 apart, right, the same thing happens. So this is the problem that it's telescoping series, and each problem looks pretty much the same. Now I want to pick up, let me just see if I can pick up something that doesn't look like this from the book, and see. In the book they are not making a big deal of telescoping series, but they should. You just need to run into 10.3. There we go. So telescoping series are explained somewhere. Page 665. There we go. Now let's see for the example in the book. Oh. Okay, I see. Well, we'll deal with that. Let's go and take a look at another interesting example. Summation, they want to start at 1, go to infinity. 1 over 2 to the k minus 1 over 2 to the k plus 1. right? That's problem 70. We are going to do the same process here, except I'm just going to use 4 terms. These are 1 apart, so the second term will start already canceling. But let's do 4 terms, even though I only need 2. Whatever. So what do we have? N equals 1. That's what it starts at 1. So the first term is 1/2 minus 1 over 2 squared, which is a 4. Plus, next term is n is 2. So I'm just going to set up 4 terms from the front, and then 4 terms from the back. So when n is equal, oh, great, they're using k's. I forgot that this book is k's. Okay, fine, whatever, k. So k is equal to 2, so that's going to be 1/4 minus 1 over 2 to the 3, which is 1/8. Then k is equal to 3. That's going to be 1/8 minus 1/16. And k equals to 4 is going to be 1/16 minus 1/32. We already see cancellations. This one cancels that one cancels this one, and here we already have the parenthesis that canceled both terms. I don't need to do anything else. I know this one is surviving, right? Everything else cancels. But, you know, since we are learning, this one cancels there, and this one would cancel in here, right? For the next one. So we see that everything canceled and only 1/2 survived. Going from the tail end, k equals n or m or whatever you want to use, it doesn't matter, right? So you have 1/2 to the m minus 1/2 to the m plus 1. The next one subtracts 1. So 1/2 to the m minus 1 minus 1/2 to the m, because you had the plus 1 and now minus 1, they cancel. Then k is m minus 2. Great. 1 over, when you subtract 2, you get 2 to the m minus 2 minus 1/2 to the m minus 1, because you had plus 1 minus 2 is now minus 1. Or you can think of the next term just subtracting 1. So k equals m minus 3, that's another previous term, right? So 1/2 to the m minus 3 minus 1/2 to the m minus 2. When you start canceling, that's gone, that's gone, that's gone. Orange, I guess, right? So what is left? What's left is 1/2 minus the limit m goes to infinity of 1/2 to the m plus 1. Well, that's 1 over infinity, and when you divide 1 infinitely many times, you get 0. So the answer is 1/2. And how awesome is that you are going to add infinitely many numbers and they add to 1/2, right? That should be something that it's completely amazing to you, right? Sitting right now, because you always thought probably that, you know, if you're adding infinity of anything, it would always add to something infinite. But here is the mathematical problem, right, which we solved, and we found that the sum is 1/2. And that's awesome. right, so now this is going to be called boss corner. All right. So summation 1 over 2 to the, they used k, right? Yeah, 2 to k minus 1 over 2 to the k plus 1. When it starts at 1 goes to infinity. Does this converge or diverge? Hey, I can use geometric series. If I break this into two separate series, because this is just addition, right? So I have this minus this. So that one converges, this one converges. And then I shift the counter. Find S1, find S2, shift the counter, S equals S1 plus S2, and you better get a half. So this could be your, homework practice problem, like a basic problem to practice, because you are shifting the counter, right? So you are practicing that part, and then you are practicing the formula for sum of two geometric series. Together they have to add to a half. So this is your first example of a problem that can be done two ways. Okay, back to telescoping. One more example of telescoping, and we're calling it quits on 10.3. What should we do? ln's, inverse tangents, square root of... Oh, we have to do a little bit more. We have to do two examples. Yeah, such is life. Okay, let's take a look at 61. Summation 1 to infinity of ln of k plus 1 over k. What, doesn't look like telescoping series? It does look to me. I know basic algebra. Let's write the formula in blood. ln of a over b is ln of a minus ln of b. Right? Yeah, that pesky pre-calculus, right? Where you have to know everything so you can survive calc. Cool. So this is 1 to infinity of ln of k plus 1 minus ln of k. And all of a sudden, I have my telescoping series. And they are 1 apart. So I don't have to go, let's go with 3 terms. Let's go with 3 terms. So, k equals to 1. Why 1? That's where it starts. It's given to you, right? So k1, k is 2, k is 3. From the tail end, k is m is m minus 1, k is m minus 2. Populate. When k is 1, we have ln of 2 minus ln of 1. When k is 2, we have ln of 3 minus ln of 2. When k is 3, we have ln of 4 minus ln of 3. Work out the tail end. Plug in m. So ln of m plus 1 minus ln of m. Take away 1. So ln of m, this parenthesis is a little bit annoying, ln of m minus ln of m minus 1. ln of m minus 1 minus ln of m minus 2. Cancel. ln 2 cancels ln 2. ln 3 cancels ln 3. Look, I have a parenthesis that has both canceled, which means that everything cancels to the right of it. Now, tail end, start from the left. I mean, from the right, go left. So ln of m is gone. ln of n minus 1 is gone. Here is your parenthesis that cancels both. That means this one will cancel in there. And we are left with two terms. Negative ln of 1, which is equal to 0, plus the limit of ln of m plus 1 as m goes to infinity. This is equal to 0 plus infinity, and we have the explosion, right? Divergence. What is ln of m plus 1? Well, that's just ln m shifted 1 unit to the left. So your graph looks like your vertical asymptote, right? And it looks like this. So as your m goes to infinity, this one climbs up to positive infinity forever. So that's why the answer is positive infinity here. 0 plus infinity is infinity, therefore diverges. So this problem did not look like something minus something else, but luckily we were able to change it, and we got it into the form where we can unleash the procedure. Now we get to the last problem. Now we get to the last problem. I'm just going to make something up so you can practice the ones that are in the book. Summation, let's start with 3. We haven't started with 3 yet. 3 to infinity. Uh, 1 over n squared plus 3n, or 2n. Does this look like telescoping series? And the answer is no, it doesn't. It doesn't look like telescoping series because it doesn't have a minus sign. Right? This is all one term. And we need subtraction of two terms. Now, this doesn't have a cute formula like ln does for us to be, up and running in the next step. So what are we supposed to do here? What are we supposed to do here? I'll wait for the chat a little bit. See if anyone recognizes it. Sometimes people do guess the procedure that needs to unfold before we can do telescoping. Anyone? I guess not. Huh? Yes! Great! Exactly. Partial fraction decomposition. So we have to crank partial fractions, and then that will give us two separate terms, and then we have to, right? So partial fraction decomposition is used here. It's going to be used again in your differential equations. So yeah, it's all over the place. So I have an plus 2a plus bn equals to 1. That's a plus b equal to 0, and 2a equals to 1. A is equal to 1/2, then b has to be negative 1/2. And this problem is 1/2 divided by n minus 1/2 divided by n plus 2. And now you just plow through calculations. Now, because this is a sum, you can actually kick 1/2 in front. Now, if you're going to forget it, then don't. You know, drag halves throughout. But I'm going to put it this way, and then minus 1 over n plus 2. And these are 2 apart, so we'll put 4 parentheses. So this is equal to 1/2 and then big bracket like this. So we have 1, 2, 3, 4. And then 1, 2, 3, 4 to go back. And the first I plug in 3, so that's right, that's my n equals 3, n equals 4, n equals 5, n equals 6. You have to start whatever the problem tells you to start. And then the tail end, n equals m, n equals m minus 1, n equals m minus 2, n equals m minus 3. So start plugging in 3. 3 minus 1 over 5. 1 over 4 minus 1 over 6. The pattern is there 2 apart, so you steal the first number here and then plus 2. So 1 over 5 minus 1 over 7. 1 over 6 minus 1 over 8. And so on. On the tail end, we have 1 over m minus 1 over m plus 2. Now take away 1 for the next one. 1 over m minus 1 minus 1 over m plus 1. 1 over m minus 2 minus 1 over m. 1 over m minus 3 minus 1 over m minus 1. Right, so you keep subtracting 1 as you move to the left. So what cancels? Well, a 5 with a 5. A 6 with a 6. Needed one more term. Next one is n7, so it will cancel this and cancel this. So those all go there. From the tail end, 1 over m and 1 over m, m minus 1, m minus 1. These two will cancel here. And we are left with 1/2 times 1/3 plus 1/4 plus the limit m goes to infinity of negative 1 over m plus 1 plus negative 1 over m plus 2. In this case, it goes to 0. Remember, previous problem, it went to infinity, right? In this problem, 1 over infinity is 0. So I have 1/2 times 7 over 12, which is 7 over 24. converges to 7 over 24. I just have to write the properties for series and we're done. All right, so let's sum up what we learned so far. Series is the sum of the sequence, and because we are adding infinitely many terms, it can converge, which means sum is a finite number, or it can diverge, meaning sum is positive or negative infinity. So for infinite series, we are literally adding infinitely many numbers, but because we can't add them all, because there are infinitely many of them, we come up with 10 tests for these series. Series will be extensively used later in your math courses and your STEM courses, 300, 400 level, right? And they are very, very important. We will see actually in chapter 11 how useful and powerful these things actually are, even now in their basic form. The goal for today is to learn 2 out of 10, and I told you that they are going to be special, and those are the first 2 that we did. So here I'll write it in blood. Why are these 2 special? Geometric series and telescoping series are the only 2 tests where we know the sum if they converge. So out of 10 tests we have in chapter 10, only geometric series and telescoping series will tell you the sum at the end of the problem. You have geometric series, you have the S formula, right? S equals A over 1 minus R. And for telescoping series, it just spits out the number at the end. So that's the sum, right? So those are the only 2 tests. Now, you will have other 8 tests. Out of those 8 tests, divergence test can't tell you convergence, obviously, hence the name divergence test, so, right? So the other 7 tests will tell you that the problem converges, but you will not know to what value. You will know that it converges, but you will not know to which value it converges. So that's why these are the 2 special tests that we learn first, because they can tell you the value it converges to. And then for the other 8 tests, those 7 that can tell you convergence, right, because one test is called divergence test. So those 7 that could tell you the convergence, they cannot tell you where it converges to. So your answer will just be, it converges by root test, it converges by integral test, it converges by p-series, right? You will just say it converges, but you will not be able to specify a value it converges to. So that's going to be for the rest of the chapter. For these 2, right, that's it. Now, let's write the properties of convergent series, and we are done with this part of the lecture. So this is a theorem 10.8 or whatever. We'll just say properties for convergent series. All right, so let summation an converge to A, and summation of Bn converge to B. These are convergent series, so they will have some kind of a number in the answer. What do we know? We know that summation of CAN is going to be CAN, which is CA. So you can kick the constant outside. Wow, what a surprise, right? We had this everywhere. You can kick the constant in front of the integral, in front of the derivative, in front of the limit. You can kick the constant in front of the sum as well. Another one, if you have a sum or a difference of these, you can split it into two sums, and that's going to give you this one at the end. So this is a good old rule of linearity. It's everywhere. And what else is good for convergence? Aha, the tail end. Okay. So I almost forgot. So let M be a positive integer. Then summation, and we'll start, let's say, n at 0 to infinity for an, and summation n starts at this m to infinity of an, both converge or diverge. Now that one is a little bit tricky to understand, but that's exactly what we did for our telescoping here, because we just defined the tail end. See, when you have, right, if you take, I just need to explain this. So if I take this one and break it into n goes from 0 to m, plus another one, n goes from m to infinity, we know that this one converges always, because this is 0 to, let's say, 100, if m is 100. So the first one will always converge because it's finite, right? So this one can be broken down into two series. And this one is still infinite series, and that one converges or diverges depending on what is in there, right? So that's why this rule over here says that whether you start at 0 or 1 or whatever, or you start at 100 or 10,000, n is always defined 0, 1, 2, 3, blah, blah, infinity. That's why you always have infinity on top of the series, right? So whether your n starts at 0 or at 3 or at 100 or 100,000, it doesn't matter, right? Because the tail end of the series governs convergence or divergence. All of the finite amount of terms that you first 100 terms or first 100,000 terms, they always can add to a number because it's a finite series. It's just 100 terms. Write a loop to add 100 terms, or sit on the calculator and add manually 100 numbers, right? But the goal, the point is that you know that it converges. It's the tail end that says convergence or divergence. So it can be broken apart. So it's just a property which was used for our telescoping series. And yep, that's it. That's 10.3. So now a quick word about the exam. So I was successful in obtaining the software and the problems and everything else to have the exam in Canvas rather than MyMathLab, which is, I hope, good news for you guys. And I am thinking of next week because we are already in the material for exam 3. That's chapters 10 and 11. So I am going to open quizzes right now. I'm actually clicking on MyMathLab and signing in to plug in to open up Calculus2 quizzes for next week so that we can be done as soon as possible with chapters 8 and 9, so that we can focus on 10 and 11 to get rid of those as soon as possible. Now, next week we are going to have office hours, we are going to have live lectures, we are going to have a review, right? So all of the bells and whistles that we need. So I'm just going to check real quick. Assignment manager. Let's see. Yes. Okay. So all of the quizzes are available. Exam 2, chapters 8 and 9. Yes. Okay, good. So I am going to right now open and the quizzes start. So exam 2, E2 quiz 1, MyMathLab, 4/10 this year, 2020, right, 6 a.m. till midnight. E2 quiz 2 on MyMathLab, 4/11, 2020 at 6 a.m. going down. So the quizzes will be available starting tomorrow morning. Please log on to MyMathLab to practice those quizzes and score points for exam 2. Now, exam 2, which is chapters 8 and 9 on Canvas next week. It will be open multiple days, so whenever you, right, it will be open multiple days, so whenever you have the chunk of time to do the exam, because the exam has to be done in one shot. You can't save and reopen, and right, once you sit down, you have to go through the exam, and then when the time expires, the exam will shut down. So you have to make sure that you are answering questions as quickly as possible, right? You don't have time to browse through videos and notes and book and looking for similar stuff, because you won't have enough time to solve the test, right? You have to answer questions because the way the exams work is they collected data on how long students take to solve problems, and they took thousands and thousands of students and data points, so we know exactly how long it takes to solve those problems. So if you are not having enough time for the test, that simply means that you are not ready for it. You were banking on having the notes and having the formulas. You had to look for those, and because you wasted time looking for examples and formulas and things, you were not solving, and obviously you are short on time. So make sure that you know the material, so when the exam starts, it's the same like in class. You have no distractions of browsing through, materials and things. You just know, and you just write it out, and you have time to do the test. So that's pretty much the way. I am going to add right from the time they recommend. I am going to add about 25% or so for checking and possible zone out and things like that. But do not bank on the that you will have enough time to go through notebook and textbook and scroll through YouTube videos and to get those problems solved. Also, another thing is if you do not learn Calculus 2, you are definitely failing differential equations. I mean, there is no way in hell you're going to pass anything in that class if you don't know, especially Chapter 8 integration, which is, the differential equation has derivatives. They have to be undone by integration. You know that in separation of variables from Chapter 9. If you are playing games, and not learning Chapter 8 because you might have reference formulas and stuff, then you effectively ended your education, because elementary differential equations, which is another elementary mathematics class, you won't be able to pass that, and without that course, you are not going to, get anywhere in STEM. Elementary differential equations are basic course for pretty much everything else, thermodynamics, chemistry, and everything is rooted physics in that course. So, and you can't do it without Calc 2. You must know these concepts. Now, in terms of exam and partial credit and show your work and all of these kind of things, you will be typing in your answers into Canvas and submitting. And what I was thinking is to ask you to take the pictures of your work and submit those in Canvas. So when I open the assignment exam 2 in Canvas, I can also request a submission. In your case, that will be a picture or series of pictures of pages with your work. Obviously, you have to be neat so I can read it, especially that it's going to be a picture and I'll be reading off of the screen and it's going to be terrible. But in order for me to assign any partial credit, I have to have the pictures of your work. So if I open the exam on Friday and close it on Sunday, that means that you have 2 days through the night to find time to sit down, hour and a half uninterrupted, to take your Calculus 2 exam 2. Now, if that's 4 a.m., it's 4 a.m. If it's 6 p.m., it's 6 p.m. But sometimes, Friday through Sunday, you should be able to do this. Now, I see over here, so the text is next Thursday. Today is Thursday. If I open quizzes on Friday, they will end on next Thursday. So yes, we can start the exam on Friday. Your quiz 7 will be on Thursday, and then I'll open, because now, guys, everything that we had for the class, is no longer applicable because we are not meeting on the regular time. I've been watching, that less and less of you are watching the lectures live. So I'm wondering if we even need to have this, since I already have like 10 sets of lectures. But I'll post. Right, I'm talking right now about 15% of your grade, and only 5 people are present, right? So we clearly have an issue, right? 5 out of 30. That's not good. I know that people will be watching this later, but maybe we don't need to have a live session then. You can just watch the videos that are already there, and then, just have office hours as interaction. Maybe that would be better than me, teaching continuously like this. So we'll discuss that in announcements. I'll turn to announcements for discussion and see which way we're going to go in the future with the class. So what I'm thinking is, and you can think of this as well, what I'm thinking is to discontinue live teaching like this, which means that you should just go and watch the videos that are already on the playlist for Calc2, or you can just type in the section, and a whole bunch of previous lectures that I gave will pop up the same way these are. And instead of having live teaching like this, we could have office hours where we all connect using Microsoft Teams, and then we can interact, right? So go to announcements. Eventually I will post stuff about the exam. We'll have the review live obviously next week. We will continue also at least 10.4 next week. If you have any questions, concerns, please make sure you are, obviously if they're private they have to go into email, but if they're concerning the whole class, make sure you're posting in discussions on Canvas under my announcements, so we can discuss all of these. So exam next week, quizzes started tomorrow. I will see you all soon, and keep checking announcements and my MATLAB homework and quizzes every day. See ya.